All right, so in this in this video, we're gonna go ahead and look at a voltage divider in the general case, and using what we've learned so far, we're gonna go ahead and derive the equation that we can use anytime we see a configuration that looks like this. It doesn't have to look exactly like this. It can look like maybe I have some voltage source plus 5 or something, and then two resistors connected like this. And then instead of trying to find this voltage, I'm trying to find this voltage. These two circuits are actually equivalent. There's no difference here if this was a 5-volt source. You will see voltage dividers drawn like this actually quite a bit, so maybe I'll throw something like that on a homework. But just want to get you used to seeing different circuits. I'll stick with what I've been doing thus far for the time being. So let's go ahead and call this Vs. That'll be my source, and then I have a resistor R1. Write that up here, and a resistor R2. Actually, I'll write that out here. I know I have a current flowing in the circuit, I, and it's going to be the same through both these resistors, obviously, because there is nowhere else for current to flow at this node. All the current that flows in is going to flow out thanks to KCL. And I'm going to go ahead and label my two node voltages. V in will be here, and then I'll label this one V out. All right. And so if I wanted to analyze this circuit using Ohm's law, I could start by looking at this resistor like I have been in the past, and I can just say very surely that the voltage across this resistor, V, is equal to V out minus 0, or just V out. And then I can say that the current then would be V divided by R, which is going to just be V out divided by R2, right? And then if I wanted to do the same with this resistor, do the exact same thing. I can just say that the voltage across my resistor is going to be V in minus V out, and then that's going to be divided by R1, and that would also give me I, right? Both expressions give me the current through the individual resistor that I'm talking about in that expression, but those currents are equal. So since this is I and this is I can actually set these two expressions equal to each other. And so that's exactly what I'm going to do. I'm going to go ahead and say that V in minus V out divided by R1 is equal to V out divided by R2. And let's recall that the goal of the previous problem, the one that we talked about in the last video, was to determine V out, the voltage here at this node, right? So we're trying to find V out. So let's solve this expression for V out. So what I first need to do is just get the expressions so that I can separate the V outs onto one side and the V in onto the other side. So let's just rewrite this as V in over R1 minus V out over R1 equals V out over R2. And so then I can add V out to the other side. That would give me V in over R1 equals V out times 1 over R1 plus 1 over R2. And now I'm trying to solve for V out. That's what I'm trying to do. So let me go ahead, and I can divide both sides by this big term here so that I get V in over R1 times 1 over R1 plus 1 over R2 is equal to V out. And this is messy, but I can rearrange this. I can do some algebra here. If I multiply the R1 in, I end up with V in times 1 over 1 plus R1 over R2 equals V out. And now all I have to do to make this look nice and to get my final equation for the voltage divider is multiply the top and bottom of the left-hand side by R2. And so now if I multiply R2 but on the bottom, the fraction goes away, and I get V in times R2, because the R2 on top will stay, divided by, and R2 is going to distribute here, R2 cancels with this R2, and then I get R2 plus R1 equals V out. And that right there is my expression for any voltage divider. To determine the output voltage, given the input voltage, I can use this expression. And so this is one that you're probably going to want to memorize. Even if you don't want to, you're probably going to end up memorizing it. And so let me just write that out one more time up here in the top corner. I'll kind of make a box for it. I think this is very important. Anytime you see a voltage divider, anything that looks like a voltage source and then two resistors in series, you can always use this equation, which states that the output voltage V out is equal to the input voltage multiplied by the second resistor, this one, divided by the sum of the two resistors. That will always hold true. This is the voltage divider, is the fundamental, one of the more fundamental DC circuits, has a lot of uses, all kinds of applications in circuits, and even in more complicated circuits, voltage dividers serve a huge role in setting bias voltages and all these very interesting things in more complicated applications. So definitely want to memorize this formula. If you don't memorize it, of course, you can go ahead and solve this thing. It makes sense. We just used Ohm's law and then set the two currents equal to each other. You can derive it yourself. And in the previous video, we figured out how to solve the voltage divider by using equivalent series resistance. And you saw that that was also relatively simple. But you will definitely want to lock this into your memory for exams. It'll save you time. And just a very useful formula that you'll use all throughout your career as an electrical engineer. And so I'm all done with this voltage divider section, and in the next video we're going to move on to what it means for two elements to be in parallel. Now we've talked about series. The next thing we're going to talk about is combining elements and specifically resistors in parallel and what it means for them to be in parallel.